Hello, this is Dennis Tribby. This is the final presentation for the Nutcracker Assembly Project for DFMA 6069. Project overview. The goal of the project is to use the fundamental principles of DFMA to reduce the overall cost of the Nutcracker Assembly. Some of the methods considered in this analysis are part reduction, materials use and design, manufacturing reduction, assembly reduction, and parasitic time reduction. What is a nutcracker? Nutcracker unit that I have on the right here basically allows a worker to load nuts into an inlet port. Nuts then get caught inside the crevice of the wheel. It rotates, in this case, clockwise up against a crusher unit, which then cracks the nut, and then the resulting nut and shells then are discharged out through the discharge outlet into a receiving bin that then gets further processed. Typical nutcrackers expect to be able to process 80 to 100 nuts per minute. Some of the requirements and guidelines that we need to follow for this project: we need to attain a 50% cost reduction. That includes material costs, part count reduction, manufacturing costs, and some associated things that go with those. Shop is expected to produce approximately 3,600 units per year, first year, 9,600 second year, and a high rate of production of approximately 12,600 units per year thereafter. The anticipated life cycle of one of these products is 8 to 10 years. Now, the recommended design must adhere to the guidelines published by the Grocery Manufacturers Association to meet food safety handling, and I will touch on that throughout the project. Now, the as-designed assembly. Notice that I have the exploded view of the assembly over here with, of course, the parts list, if you will, with the materials and the quantities. There's 6 designed part numbers. There's a front and back cover. Here's the front cover, the back cover, the crusher itself, the wheel, that where the nut falls into rotates against the crushing unit, the drive shaft, which turns the wheel, of course, the return bracket, and then the delivery bracket. That's effectively the names. We can call them the right-left bracket. Now, there are 2 covers, the front cover and the back cover. They're identical at this point. All of the design materials here are made out of 304 stainless. There are 4 part numbers that are purchase parts. You would have the pinion roller bearing, which is this bearing here and this one here, and this becomes the pinion itself that's manufactured. Then you have the drive shaft roller bearing at the top and the bottom. Then you have 4 bolts and 4 nuts. Those are all purchase parts. There's a total of 10 unique part numbers and a total of 19 actual individual parts itself. Listed on here also as designed is tolerances are defaulted to 2,000th unless otherwise stated, with surface finishes at 16 microinches. Now let's look at the cost per unit. So total cost for one unit is $4,088. That's based off of the actual stock cost, the cost of the labor, which has been estimated through the flow plans, and any outsourcing costs. So you get the total cost of each part for the total assembly. Then you have the purchase parts. It adds up to $4,088. Now, the material cost represents over 50%, which is $2,183. And the outsourcing operations, which you can tell are for the covers and the right and return brackets, is $1,775 for 44% total cost, with a work in process time of 9 to 17 days. And that's based on all of the outsourced manufacturing that we have done. So clearly, there's some room for movement along these. Now, critique of the as designed. So based off what we just reviewed, it's pretty clear the part count's pretty high. I think it's pretty high. If it were a jet engine, it'd be real low. It's a nut crusher, maybe it's high. But looking at the exploded view, you can clearly see that we have some purchase parts for fasteners whose sole purpose is just to hold the thing together. Probably a better way to do that. And also, it's pretty clear, I think, that looking at this, that we might be able to combine some of the actual manufactured parts to form a single base type unit. The material choice for this is 304 stainless steel for all the manufactured parts. 304 is a pretty expensive materials we'll review in just a moment. It's also very difficult to machine because the hardness and the manufacturability ratings are a little bit high. Also want to take a look at the tolerances and surfaces finishes. They seem pretty tight for the entire assembly. Certainly the drive shaft and the internal wheel where the drive shaft pins presses in, that probably needs to be pretty tight tolerance, but the rest of it could be loosened up, I think. Also, manufacturing processes are very expensive. Noted in the process flows, the actual front and back plates and the right and left return are water jet cut, which is a very expensive process that is also expensive when it comes to parasitic time for lead time. So let's take a look at some of our design recommendations. Well, the first thing we want to do is do part reduction. So in this case, we're going to take the return side, the right side, and the bottom plate from the assembly. This is just a cut of that. And we're going to combine those into a single unit. We're going to use cast to create this. I'll talk about that a little bit later. But instead of these being straight from bar stock, then water jet cut, and then all the grinding and milling to get it to these individual pieces, we can actually do a water glass cast on this, and we can cut it drastically. I mean drastically reduce the price of this. We'll also reduce the part count by 2, so instead of there being 3 separate part numbers here, we'll have 1 new base plate number. We can also eliminate some of the purchase parts. It's not a pure elimination because we're actually going to add some stuff back in, but we can get rid of the 4 quarter 20 bolts and the associated quarter 20 nuts. We reduce those completely, and what we can do is replace those with 4 quarter 20 thumb screws, which will require us to tap in 2 inches on the corners, same location as where they were before, so we can thumb screw these in. I like this idea temporarily at least because it means I don't need a tool to tighten the nuts and bolts up. I can just thumb screw these in and it takes them out a little bit quicker. So let's take a look at the part reduction list. We can see here that we're effectively going from a quantity of 7 manufactured parts to 5. That's about a 29% reduction. 6 part numbers to 5. Even though that's not quantity, that's important because now there's less tracking, there's less bookkeeping in the background, we have less inventory, we got fewer bins. On the purchase parts, similar situation. We're going from quantity of 12 purchase parts to 8, 33% reduction. And we're going down to, instead of having 4 unique numbers, we're really just down at this point to this should be 3 unique part numbers. Sorry, that would be a 33% reduction. The next thing we're going to take a look at is materials. Now, the materials change. This is a little bit of a homework problem. You have to kind of look at a lot of different angles here if you review the GMA guidelines and food safety guidelines. And what we look at is we can find and we can narrow down to the steels, stainless steels, and certainly we could look at aluminum as well. But we look at the 4 candidate steels that I chose, 303, 304, 316, and 430. And I wanted to kind of do a listing of the Brinell hardness test, manufacturability, and the price. Now, price shouldn't be the only driver. You need to look at a few other things because if manufacturability is very, very poor, then the price per pound is sort of not as big a factor because the machinability is high. After looking at all this, I came to the conclusion that 430 stainless, it fits GMA guidelines, food safety guidelines. It's got a hardness rating of 147, less than 304, 0.65, a little bit easier to manufacture, work with, and it's significantly cheaper than the 304 stainless. So I think that's the choice to go with initially off this. So all the design parts, of which there's now 5, we're going to change to 430 stainless. Now, let's take a look at the manufacturing process. We've combined our parts, we've got our manufacturing parts list, we've got our materials that we've chosen, we know what our quantity is. The next step is I think we have to decide how we're going to manufacture these. So I think for the crusher, the wheel, and the drive shaft, I don't think it makes sense. These are kind of detailed. There's turning processes on the crusher. Wheel's fairly complicated. The drive shaft has to be turned at a pretty tight tolerance. So I think I'm going to not change the process for those. But I think on the crusher and the wheel that we can actually loosen up the tolerance from 2/10 thousandths to a hundredth of an inch on each of these, plus or minus. Now for the front cover and the rear return cover and delivery combined base unit, I'm going to go with I guess we'll go with a water glass cast mechanism. So we'll do casting for these. These are per part castings. We don't need to create a die cast for this. And I can cast pretty high level rate of production. This is a pretty common process. And this casting is really going to drop the cost down quite a bit. So effectively, we're going to go with casting for the front cover and the return cover delivery combined base unit. And we're going to reduce the tolerance from 2,000th to 100th. And we can also change the surface finish from 16 to 32. Again, for this casting process, 32 is perfectly acceptable. Let's take a look at our cost here. Now that we're going to decide how we're going to work with this, the total savings for the redesign of Nutcracker assembly is approximately $3,574, which represents a reduction of 87.42%. It also reduces our parasitic time down from 9 to 17 days to reduces it down 6 to 11 days, taking it down to 3 to 5 days. This is pretty dramatic. So the unit cost now to produce one of these is approximately $514 per unit. Again, that's an 87% reduction in cost, which certainly meets our high-level requirements. I think the next thing we want to look at is changes to the shop floor layout. Since we're not doing so much grinding and milling, I think what we can do is we can have our incoming parts, this would be the purchase parts and the outsourced parts, come in. They would get held into inventory until they're needed. But I want to open up the shop floor a little bit so that we can now have parts that could go straight to assembly. They could go straight to depending on the part, we have a little bit more access. So instead of grinding being the center of the operation, I want this to be more of a single flow type shop floor. Now, having said that, there's a lot of questions that need to be asked. Not a lot, but a few questions. And the first question I want to ask is, will the nutcracker be used to crush various varieties of nuts? Now, depending on the answer, if they say, nope, we're strictly doing walnuts, it's basically, the same range of diameter of nut that it's going to be. If that were the case, we may decide to go ahead and bring that crusher pin and make that part of the base unit. That would cut out 2 bearings and alleviate the crushing pin itself, and then we could still cast that all in one piece. That, I think, would reduce cost a bit more. In that case, it would also alleviate the fact that we have 2 bearings that aren't the same size bearings as the drive shaft. Now, if they say, well, we need to keep that pinion in here for the crusher, if that were the case, I may switch the bearings out to make them the exact same size bearing as the drive shaft bearing, so I could reduce one more part number. Now, the next question is, do you have flexibility with your workforce for cross-training on different machines? Again, the operations have changed. There's not so much milling and grinding as there was since we're casting these parts. We may need these people to become, you certainly wouldn't move a manufacturing machining guy into assembly, but there's other areas, finishing, and there could be some other things that we use them for. Also, does the shop floor have any obstructions preventing a more optimized design? I was reluctant to change the shop floor too much. I've been around shop floors a lot. You just can't move things around as easy as you think. There's a lot of obstructions and posts, and there's reasons things are where they are. So I'd kind of like to find out a little bit more about that. And lastly, would you consider reviewing the table mount system for possible improvements? I'd like to look at the whole assembly, not just the nut assembly itself, but the whole mechanism to see if somehow what we're doing at this level allows us to modify something else to make it better. Some designs may talk about thinning the crusher unit down from 4.5 inches to 3 inches. Well, that suddenly modifies the amount of nuts that it can crack. So there's questions that need to be asked there. Again, effectively, the last 2 slides basically get into the casting cost process itself. That's all I have. That's the end of the presentation, and I thank you.